Just learn something new. All right. So welcome YouTube. This is Beautiful Mind here, and we're going to be doing I'm just doing a late night stream so that so my intent for doing it at this hour is so that during class time I can just be available for questions, right? Yeah. So like with the OBS, when I first logged on, I didn't know that like when you switch between scenes, it saved your audio settings as well. So I just learned that just now as I kind of switched around on OBS. But yeah, so this will be our week 3 Monday lecture for applied statistics. One thing to kind of to note, let's hop over here to Moodle. Let's clear out a lot of this stuff. All right, this looks a little bit better. So for Moodle here, we'll notice that there is this participation in academic honesty verification. We need to take that quiz, okay? So log into Moodle and go ahead and take that. Just that needs to be submitted, okay? All right. So I think exam one was due this past Saturday at 11:59. If you didn't get it in, don't fret. You can actually submit all of these assignments past the due date, but there'll be a penalty. But there is a final deadline, like towards the end of the quarter. So, and keep in mind that as we get closer to deadlines, Pearson will shut down, like because everybody's going to be on it at the same time. It's just not going to work. That's throughout the years. Is one thing that has been consistent is that it typically shuts down at the last minute. So I said it to say, you want to do your best to kind of stay current and like get your assignments submitted as soon as possible. If you try to wait till the last minute, it's going to lock out, and that's not a good look. Also, so with late assignments, the highest you can make on any late assignment is a 80%, and the highest you can make on any late exam is a 79%. So on like homework and quizzes, the highest you can get is a B. On an exam, if it's submitted late, the highest you can get is a C. So the best thing is do your best to get it submitted early. Get it submitted early. I totally do not get how the Snapchat thing works. Anyway, not gonna worry about it. Yeah, I'm totally don't get it. Anyway, so I can't think of any other announcements. I would say for this week, be on the lookout for a quiz, maybe towards the end of the week. And just honestly, any assignments that you see on Pearson, especially if it has a due date, you just want to go ahead and get those submitted. Okay. And again, as you have questions, you have to write them down and reach out to me to get them answered. So again, my intent is to load these videos early so that way during class time, I could just be available for questions. Okay. I think we're going to be moving into chapter 3. So today, for right now, I just want to go through section 3.1. There it is. 3.1 Basic Concepts of Probability and Counting. Okay. So some objectives here are how to identify the sample space of a probability experiment and how to identify simple events. How to use the fundamental counting principle to find the number of ways 2 or more events can occur. How to distinguish among classical probability, empirical probability, and subjective probability. How to find the probability of the complement of an event. And how to use a tree diagram and the fundamental counting principle to find probabilities. So a probability experiment, an action or trial through which specific results, counts, measurements, or responses are attained. That's what we mean by a probability experiment. An outcome is going to be the result of a single trial in a probability experiment. The sample space is going to be the set of all possible outcomes of a probability experiment, and the event is going to be one or more outcomes and is a subset of the sample space. Okay. All right. I don't want to see the solution. All right. So this example says a survey consists of asking people for their blood types O, A, B, and AB, including whether they are Rh positive or Rh negative. Determine the number of outcomes and identify the sample space. So then we have these 4 blood types. and then they could either be RH positive or RH negative. So they can be what? O negative, O positive, A negative, A positive, so on and so on. So for each of the first choice, we have 2 of the second. So this is an example of the multiplication rule. So since we have 4 choices in the first step and 2 choices in the second, then 4 times 2, it should be a total of 8 possible outcomes here. So a tree diagram gives a visual. So let's look at a tree diagram. So here we see that, you could be O positive or O negative, A positive, A negative, B positive, B negative, or AB positive, AB negative. You see the 8 choices here. Okay, is there another example? So a simple event, an event that consists of a single outcome. For example, tossing heads and rolling a 3. So you get a heads and a 3. An event that consists of more than one outcome is not a simple event. Tossing heads and rolling an even number. Okay, I'm going to let that be for right now. Right here. So we're asked to determine the number of outcomes in each event, then decide whether each event is simple or not, and explain the reasoning. For quality control, we randomly select a machine from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So if we want one specific defective machine part, there's only one possible outcome. So yeah, there should be only one outcome. So this event should be simple because there's only one outcome. Okay, let's try the next one. Same thing, determine the number of outcomes in the event, then decide whether each event is simple or not, and explain the reasoning. We roll a 6-sided die. Let's see, event B is rolling at least a 4. So if we have 6 possible outcomes in the sample space, event B is rolling at least a 4, so that means we can get 4, 5, or 6. There are 3 outcomes in this event. So this event is not simple because we have more than one outcome. All right. So then we have the fundamental counting principle. If one event can occur in m ways and the second event can occur in n ways, the number of ways the events can occur in sequence is m times n. This can be extended for any number of events occurring in sequence. Okay, so if we have one thing, so I usually see this, like we actually did one, like this is the one we did, the first one that we did, where if we take for each outcome in the first step, we have, so many for the second. So the same amount for the second step or a similar number. They all have the same number of outcomes in the second step. Then that's, one thing happens and then the second thing happens. That's an example of fundamental counting principle. I refer to this as the multiplication principle. Let's see this in action. Okay. So we are purchasing a new car. The possible manufacturers, car sizes, and colors are listed in the table. How many different ways can we select one manufacturer, one car size, and one color? Okay, so here, notice for each choice in the first step, we have 2 choices in the second. But then for each of those, we have 4 choices in the third step. So then this is an example of the fundamental counting principle. So basically we just multiply. It's going to be 3 times 2 times 4. 3 times 2 is 6 times 4 is 24. There should be a total of 24 different combinations that we can do with this structure. Let's see, 24. So if we were to choose a tree diagram, first we have to choose the manufacturer, right? So Ford, GM, or Honda. Then we can choose either compact or mid-size for each one, right? And then for each of those, we have 4 choices for the color. So then we get something like this. So then we have a total of 24 different cars that we can choose from. Oh, okay. Yeah, I just didn't want to see the answer. Example, using the fundamental counting principle. The access code for our car security system consists of 4 digits. Each digit can be any number from 0 through 9. How many access codes are possible when each digit can be used only once and not repeated? Okay. So let's go with this first one. So we're doing an access code for a car security system. It has 4 digits. Each digit can be any number from 0 through 9. So it says that how many codes are possible when each digit can be used only once and not repeated? So in the first box, we have a total of 10 choices to choose from, right? We have 10 digits to choose from. So then we choose a digit. We've chosen one and we're not putting it back, so it can't be repeated. So then now in the second step, we only have 9 choices. So in the first step, we had 10 choices, but then for each of those, in the second step, we're going to have 9. But then for each of those in the second step, we're going to have 8 choices in the third, and then 7 in the fourth. So then this is the fundamental counting principle. So then we would multiply these results, whatever that multiplies to, all right? So 10 times 9 times 8 times 7. You see it here. 10 times 9 times 8 times 7, okay. The second one, it says that each digit can be repeated. So if each digit can be repeated, the first step, we still have 10 choices. But then since it can be repeated, that means in the second step, we're going to have 10. Third is 10. And the fourth is 10. So we're going to have a total of 10,000, 10 to the power of 4, which is 10,000 possible codes. And then the third one says that each digit can be repeated, but the first digit cannot be 0 or 1. So they can all be repeated, but in the first step, instead of having 10 choices, we have, 8 choices. So then that one is going to be 8,000 codes. So we're looking for 10,000 and 8,000. Let me clear this out. You see the 10,000, we see the 8,000. Okay. Give me just a moment. I'll be right back. And we're back. Okay. Yeah, it looked like it worked. Maybe not. Let's turn this down. Maybe if I do it different. I don't know. I'll figure that out later. But I know that they can do it. Okay. So moving along. Okay, we're gonna let that be. So then we have some types of probability. So we have classical theoretical probability. Each outcome in the sample space is equally likely. Okay. And the probability of an event is going to be the number of outcomes in that event. The number of outcomes in that event divided by the number of outcomes in the sample space. Okay. Don't want to see the solution. So in this example, we roll a 6-sided die. Find the probability of each event. Event A is rolling a 3. So in the 6-sided die, how many 3s are there? Well, there's only 1 3 out of a total of 6 outcomes. So that probability is 1 out of 6. Rolling a 7 on a 6-sided die, well, there are 0 7s on a 6-sided die out of 6, so that probability is going to be 0. Rolling a number less than 5, there are 4 numbers less than 5, 1, 2, 3, 4. So 4 out of 6, which is 2/3. Okay. I'm going to clear these out. One out of 6, 0, and 2/3. So that was an example on classical probability where each outcome is equally likely to occur. With empirical or statistical probability, it's based on observations obtained from probability experiments. It might be the relative frequency of an event. The probability of an event is going to be the frequency of the event, so how many outcomes in the event over the total number of outcomes. Okay. So in this example, it says a company is conducting an online survey of randomly selected U.S. adults to determine how they read books during the past year, if at all. So far, 1,490 adults have been surveyed. The pie chart shows the results. Note that the digital book includes ebooks as well as audiobooks. What's the probability that the next adult survey read only printed books during the year, last year? So if we look at the chart, it says read only print books was 587 out of a total of 1,490. So then the probability of this event is going to be the 578 over the 1,490. $578 over the 1,490. Okay. Let's go let that be. Okay. And this example says a company is conducting a phone survey of randomly selected individuals to determine the ages of social networking site users. So far, 975 social networking site users have been surveyed. The frequency distribution shows the results. What is the probability that the next user survey is 23 to 35? So we see 23 to 35 is here, and the frequency there is 312 out of a total of 975. Oof. So then the probability of someone being in this range is going to be the 312 over 975. You see it here. So it's going to be this. So then we have this thing called the law of large numbers. As an experiment is repeated over and over and over, the empirical probability of an event approaches the theoretical probability of an event. So in the theoretical sense, if you toss a coin, it should be 50-50 to get a heads or a tails. A fair coin, it should get a 50-50. But if you actually run the experiment, say you toss it 10 times, you might have like 7 heads and 3 tails. Right? So then those probabilities are going to be skewed. But the more you run that experiment, the closer and closer each probability will get to their theoretical probability. All right. So the application might be different than typically is different than the theoretical, but then the more the experiment is run, the closer those outcomes are going to get closer to the theoretical probability. Let's see. So then the final type of probability that we have is subjective probability. It's based on tuition, educated guesses, and estimates. It's not really based on any data. It's just how somebody feels about something. For example, a doctor may feel a patient has a 90% chance of a full recovery. Right? So they're not really basing it. It's just like an educated guess, but it's not like based on data. Okay. So these next few examples, we want to classify the statement as an example of classical probability, empirical probability, or subjective probability, and we're asked to explain our reasoning. The probability that we will get an A on our next test is 90%. So for me, that would be subjective probability because it's not really based on any data. It's based on how we feel. So it says the probability that a voter chosen at random will be younger than 35 is 30%. So more than likely that's going to be based on some data from like a survey or like at a polling location. So that would be an example of empirical, like because it's based on observations like an experiment or a survey. All right, so I would say empirical there. Okay. So this one is on the probability of winning a 1,000 ticket raffle with one ticket is going to be 1 out of 1,000. So we have 1,000 tickets. Each one has a probability of 1 out of 1,000 of winning. So that's an example of classical probability. Okay, this section looks like it's going a lot faster than I anticipated. I might go ahead and do 3-2 as well. I think I'm gonna just let this be. This will be enough for right now. Like I think this is enough. As long as but I do want to finish chapter 3 by the end of the week. So I might come back and do another just bonus lecture just to kind of, keep the pace of rhythm. I think I'll let this be. I'll just stop here for today. But again, I do plan on being available during class time for questions. Okay. If I feel up to it, I might just go ahead and do 3-2. But right now, I'm kind of like faded. Let's kind of keep going though. So range of probabilities. The range of probabilities rules. So the probability of an event is always between 0 and 1 inclusive. So if the probability of an event is 0, then it's impossible to happen. Versus if the probability of an event is a 1, it's guaranteed to happen. If the probability is 50%, then is equally likely. It's an even chance of it happening. It's equally likely and unlikely to happen. If it's less than 50, it's going to be unlikely to happen. If it's more than 50, it's going to be likely to happen. So what do we mean by complementary events? The set of all outcomes in the sample space that are not included in the event. So say we have the sample space, which are going to be all the outcomes of an event. And then we have an event which is going to be a subset of the sample space. Then the complement of this event is going to be denoted as E prime or E complement. And it's going to be everything inside the sample space but outside of our event. Okay. If we take the probability of our event plus the probability of the complement, those should add up to 1. And then through algebra, you get these other 2 results. So in this example, we're asked to find the probability of randomly selecting a social networking site user who is not 23 to 35. Who is not, right? So we're going to use the complement rule. If the probability of them being 23 to 35 is 312 divided by the 975. So this question is essentially asking us for the complement of this event, the opposite of this second event here. So all we're going to do, we're going to take that probability, this divided by this, we're going to say 1 minus that probability. You see it here. 1 minus that probability is going to be this. We could have said this probability plus this one plus this one plus this one, and we'll get the same result. But that's just an example of the complement rule. I just don't want to see the solution. Okay. So in this example, it says a probability experiment consists of tossing a coin and spinning the spinner shown. The spinner is equally likely to land on each number. We're asked to use a tree diagram to find the probability of each event. Tossing a tail and spinning and getting an odd number. So if we're going to do a tree diagram there, tossing a coin and spinning the spinner. So we could either have a heads or a tails. And then it looks like we have 8 outcomes, right? So we can get, let me see, 1 through 8, 1 through 8. Let me see, I'm gonna go 4 and 5, 2, 3, 6, 7, 4, 5, 2, 3, 6, 7. So that could be any of these. This could be any of these. So event A is tossing a tail and getting an odd number. So what are the outcomes that are tail and odd? So what we can have T1, tails 1, tails 3, tails 5, and tails 7. So it looks like, so then there are 4 out of a total of, what is this? 8 times 2 is 16. So that probability should be 1 out of 4. Let me duplicate this page. Okay. Tossing a head or this, let me see. Tossing a head or the spinner spinning a number greater than 3. So basically all of the heads will be included in that. Is it or spinning a number greater than 3. So that means we have these. So it's these 8 on the far left. So we're going to include all of these. We're also going to include greater than 3. So that means these guys over here. So then 8 plus 1, 2, 3, 4, 5. There's a total of 13 there. So then we have 13 outcomes there out of a total of 16 outcomes. Okay, let's see how do we do. We got 1 out of 4 and 13 out of 16. So you see the 1 out of 4 there. You see we kept all the heads and everything on the right except for the first 3. 13 out of 16, you see it there. Okay. I think this is going to be our last example. It says our college identification number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What's the probability of getting our college identifier number when we're randomly generating 8 digits? Okay. So let's see. So we have 8 slots. So 1, 2, 3. Okay. So it says our ID number consists of 8 digits. Each digit can be 0 through 9, and each digit can be repeated. What's the probability of getting our ID? So we only have one ID on this campus, and it says 0 to 9, so there are 10 choices, right? So for the first digit, we have 10 options, 10, 10. All of them are 10 because they can all be repeated. So then that's going to be 10 to the power of 8 possible outcomes. So then the probability of this event, we only have one ID out of a total of 10 to the power of 8. And that's our answer. So that's the probability of pulling our ID out of all of them. Notice we have 8 zeros here. 3, 6, 7, 8. So 1 out of that. Okay. Let's see the time. Yeah. Okay. So I'm actually going to go ahead and end the session there. So what we want to do, we just want to take this time to kind of make sure that things are in order. Go ahead and get started on homework for Pearson. I'll go ahead and load. We just did what, chapter 3? I'll go ahead and load, and let me go ahead and send a copy of this to Box. Handwritten notes, not college algebra. So also there's a quiz. Oh, okay. I guess I didn't. Well, I'll just send it there anyway. Oh, matter of fact, I think it's a different location. I need to delete that second one. I don't know how there are 2 copies. Yeah, that's the right one. So yeah, there is a participation in honesty quiz that's on Pearson. You definitely want to go ahead and do that. Okay, so you can take time now, or just as soon as possible to go ahead and get that submitted. We're gonna actually go ahead and end the session here, and from one beautiful mind to another, enjoy the rest of your day. But again, we're supposed to meet. I'll just be available for questions during class time, and just kind of keep working on the assignments that are on Pearson. Also, be sure to submit the participation and honesty quiz. And have a wonderful day.